Hi everyone, I'm Pranoti, your host of Under the Microscope, and today we have Under the Microscope. You will understand the pun later on, but today we have Levi Tegg, who is a research associate at the University of Sydney, and he lives and breathes microscopes and under the microscope and everything. So please join me in welcoming Levi. Hi Levi, how are you?
I'm very well, Pranoti. How are you? Thank you for having me today, by the way.
I'm so happy to have you. It's like your wall in behind you for anyone who is watching this video on YouTube. Oh, like it cannot get more. Is it meta? That under the microscope, like yeah, kind of. Yeah. Okay, so tell me about your research in super simple words, please. Like super simple, like anyone who does not live and breathe microscopes and electron microscopes can understand. So tell me.
For sure. So my research is to use microscopes to study all sorts of materials. Okay. Microscopes includes things like the optical microscopes you would have used in school, electron microscopes of various types, and the atom probe microscope, which is a particular type of atomic scale 3D microscope. I use these microscopes to study materials like steels, nanoporous metals, ice, metal oxides, just to understand how their structure causes the properties they have at the big scale.
Okay. You mentioned you study ice. Like, why do you study ice? Why do you have to study ice? I mean, we know what ice is. What are you going to change in the ice?
Amazing question. So I'm studying ice using the atom probe microscope, not because ice on its own is particularly exciting, but ice is the environment where biological materials live. It's the solution of life, proteins, DNA. And so cryo-TEM is a workflow that allows us to look at things like proteins and DNA using the transmission electron microscope. My current role is to sort of take that idea and apply it to atom probe microscopy so that we can get 3D atomic maps, not of water and ice, but of the proteins, DNA, and other biological materials which natively exist in water/ice.
Aha, okay. Oh, that's interesting. Oh, so it's not about okay, got it. So, but the 3D information you can also get from a TEM or a SEM, like with electron microscopes, right? Why use atomic probe microscope?
The data that comes out of the atom probe microscope has some kind of big differences between SEM and TEM. So first, it's an atomic scale technique. You get data atom or at least small cluster of atom at a time. Second, it's natively three-dimensional. It's not like tomography, like in the TEM where you have to tilt the sample. In atom probe, the data is naturally in 3 dimensions. So together, it's 3D near atomic scale reconstruction. The third big advantage is that it also natively gives you microanalysis. You don't know that an atom popped off, you know what atom popped off. Carbon, nitrogen, hydrogen can all be seen with equal sensitivity in the atom probe microscope. So not only do you know where the protein is and what its structure is, if we do it right, we can hopefully see what every atom in the molecule is and its original position. Perfect microanalysis of the molecule.
I feel like I have to visit your lab, your Center of Microscopy and your sister facility, because this is Candyland for me. As someone who loves microscope, especially electron microscopes and all kinds of microscopy. It's amazing. So Levi, how did you end up being the microscopy ninja that you are? How did this happen? Tell me about your journey in science so far.
Yeah, for sure. So I did a Bachelor's of Science in Physics in my hometown at the University of Newcastle. And as part of an undergraduate summer program, I had the opportunity to learn the transmission electron microscope as an undergraduate for a 6-week period over the summer. And I fell in love. I had so much fun using this microscope. And so I stayed with physics and I started doing a PhD in physics, or although it was delivered by physics, it was more broadly described as materials science and materials characterization. I used X-ray diffraction, scanning electron microscopy, and transmission electron microscopy to understand complex metal oxides. And based on the skills I developed in my PhD, I got the job that I'm in now at the University of Sydney in the Australian Centre for Microscopy and Microanalysis, where I'm lucky enough to use microscopes almost every day. So now I study not only the complex metal oxides from my PhD, but through collaborations, I've come to study all sorts of different materials, like the ice I described earlier, steels and alloys, all sorts of other things.
That is so cool. It's very similar to my journey in science as well. I got the opportunity to do an internship during my bachelor's, like during my undergrad, for like it was 2.5 months or something. And that was the first time I was introduced to electron microscopes, and it was like love at first image, literally.
Oh, love it. Fantastic. So good.
There was no going back, and it's there is no going back. Okay, that's awesome. So it's very, very interesting. So now in your current role, you don't just work on like one material, but you get the opportunity to work on several different materials and with different labs, different groups, answering different sorts of questions. So it sounds to me that you are involved in a lot of interesting and fascinating research projects. So if you have to pick one research project that you're most proud of, one of the most, okay? It's a mean question. I know you do not.
A very mean question. Choosing my favorite child.
Exactly. Let's say, who is your favorite child today? Yeah, let's not like, let's just go with that. So could you explain it to us? Pick your favorite child and explain everything about that child in super simple words in the section we call In Other Words.
That's such a hard question because I've got so many projects that I'm so fond of.
Of course.
I think I'll actually go back in time. I'll go to the project which I have most maturely explored, and there's the work from my PhD studying these complex metal oxides.
Mm-hmm.
In my PhD, I studied these perovskite-like oxides, which, although metal oxides are usually insulators, these metal oxides were conductive. Gave them interesting applications in nanophotonics, which gave them more applications in catalysis and all sorts of other things. Mm-hmm. My project was to study their synthesis, everything we can possibly find out about them at the new atomic scale, and some applications. So I did all sorts of really cool experiments. Like the one that springs to mind is we make these metal oxides sort of like making a cake. We mix all of the reagents together, push it into a pan, and heat it up in an oven, except it's like 800, 900 degrees rather than 220 for 30 minutes. And the literature, when we started the project, said you needed about 8 hours to complete the work. But some experiments we had done, we found it was taking more like a couple of minutes. But we wanted to know just how fast. Now, this is not microscopy, but microscopy later, I promise. To find out how fast it actually took, we were lucky enough to get some time on a neutron source to do neutron powder diffraction. It's just like X-ray powder diffraction, but with neutrons instead. So it's a bit harder to get to, particularly in Australia. Uh-huh. And so what we did is we mixed our little cake batter together, and we put a furnace into the neutron beam, and we literally dropped our samples into the furnace, into the beam, to heat them really quickly, collect patterns every few seconds, and see what would happen. And in our first few experiments, we watched the patterns change every 30 seconds or so, and then all of a sudden the reaction was complete. It was done. We were shocked. We thought, oh, it's faster than as fast as we're collecting patterns. So we had to do more experiments. We'd change our experiment plan while we were there to bring down the time sampling period. And the reaction was done in like 15, 20 seconds. So much faster than we thought, and way faster than the literature made it seem. That sprung to mind as an experiment that was really cool because it used brand new equipment on high-end research infrastructure and found something totally different to what the literature was expecting. Uh-huh. That project was also overflowing with microscopy, like those metal oxides naturally grew as these beautiful little cubes, looked like dice, I suppose, which looked beautiful under the SEM and the TEM. Oh. You could change the synthesis conditions and get these rods, look like bundles of sticks, beautiful stuff.
Oh,
There's
wow.
a lot of fun material science and characterization in that project.
That sounds so cool. That sounds so cool. So I hope you published that work other than just
We did.
your PhD work that, hey, you don't need 8 hours. All you need is 15 to 20 seconds, however longer.
We submitted a journal cover and they accepted it. So although, microscopy is known for its pretty pictures and neutron diffraction is not, we were still able to get a pretty picture out of the neutron diffraction on the journal cover for that issue.
Oh my God, that's so cool. Which journal cover are we talking about here? You can name drop. It's okay.
Journal of Physical Chemistry C, sometime in 2021. Unfortunately, I don't remember the issue number. Guilty.
That's okay. That's okay. I'm sure you will show it to us, your followers, and we are talking about on the Real Scientist Nano Twitter account. So,
yeah, can't wait.
And how was the response of the research community then? They must have been like, what?
That's a hard question. I didn't see that one coming. Well, the reality is it actually hasn't been cited more than a couple of times since 2021. So the impact was a lot less than you think.
Okay. Did you talk about this paper at different conferences?
Well, as soon as I published this paper, as soon as we did this experiment, we entered the coronavirus era and conferences were all essentially shut down. So although I had abstracts ready to go to present them, I didn't actually attend any conferences related to crystallography and this sort of metal oxide material science after my PhD. So unfortunately, no, I haven't had a chance to present this exact work at any conferences.
Okay.
It's a big shame. Always regretted it.
Okay, let's try to change that when you're taking over the Twitter account. This is like a game changer, right? Because going from 8 hours to 15 seconds, that's a humongous amount of time that can be saved. And not just time, but also resources, because it takes a lot of energy to keep the oven or the pan going for 8 hours at 800, 900 degrees. So this is amazing. Clear to me that you love the research aspect of being a scientist, using the microscope and making a cake, all of that. So what else do you like about being a scientist?
You're absolutely right. I love the research part. I love the sense of discovery. I love using cool tools. Other than the research part, I think the part that excites me is the sense of community and collaboration. Academia and science has such a huge emphasis on collaboration and attending conferences, and it is not without merit. You learn so much just by going to other laboratories and going to conferences and seeing maybe something you already knew but explained in a whole new light, and afterwards talking to somebody working in the same field and realizing that either they're struggling with the same thing as you or they have already struggled and they already know the answer. So I think that the ability to science's emphasis on collaboration and connecting with other like-minded scientists is one of the greatest strengths of the field. With academia, it's not secretive, it's collaborative. I think that's something that's really great about it.
The sense of community and the sense of collaboration, I think that's amazing. So it's been going well for you. Now tell me what you would like to improve. So if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay? You can ask for all the microscopes in your basement. You can ask for anything. Ooh, okay. So 3 wishes.
Yeah. Okay. So in the Australian tertiary sector, there's this increasing casualization of teaching and research staff. And I think that if I had my biggest wish for the Australian academic sector would be more ongoing positions of all types. Academic research, teaching, academic teaching, technical. A lot of these positions are contracted, but I think that a lot of people would probably prefer them to be more ongoing. So adding some certainty to people who may be in the same role year after year. But I think everybody wants that. Everybody wants more ongoing positions in academia around the world. That's not really special.
I mean, you can always highlight it that even in Australia, this is a need, this is a wish. So even if it is like a commonly known wish, it's always good to reiterate it and say that, hey, I also would like to do that. So, okay, that's the first wish. Second one.
Second wish. I think that this is getting a lot better in recent years, but something that I think Australia could really do with is a more diverse funding landscape, more funding opportunities, more targeted funding opportunities, and funding opportunities that are maybe smaller with quicker turnaround times. Although it would be harder for any researcher to keep on top of all the new funding opportunities, I think that it's good to have a diversity of different types, not just large multi-year projects, not just small travel grants, not just for travel, not just for consumables. More funding opportunities and diverse funding opportunities, I think, would be really, really great. But like I said, I think it's gotten a lot better even in the past few years.
Interesting.
Third one, gosh, that's a hard one. I reckon a dedicated coffee shop just for our microscopy facility. I think that the benefits to work-life balance at my institute would be greatly improved by having a coffee shop and a barista specifically dedicated to our department.
Okay, coffee shop and barista. Okay, you took it one step further. That's really. I was like, I mean, we have had like decent coffee machine sometimes, but a barista, that's actually a good.
Australians are real coffee snobs. So
okay.
a coffee machine on its own wouldn't cut it. You need a trained barista, you need single origin, you need the whole coffee shop experience.
Yeah, that makes sense. And that's also a great place for discussions, right? Because oftentimes I think collaborations and best ideas.
Yes.
Okay, let's try to make that happen. So give me the email address and name of the lecturer of your institute, and I will cut it and send it to them. That is.
Honestly, your point about being a place for collaboration makes me wonder if I can walk in there now and get it done. Like maybe there's already enough of an argument.
Yeah, absolutely. And maybe whoever the person in charge is, they're already thinking about it. They just don't get the request officially to do it. So,
Exactly.
You mentioned about the different sorts of grants. So do you, like in Germany, I know we have this, you can apply for research grants from the state or from the country or from the EU, which go for like 3 years, 5 years, and that includes everything. Like there is a budget for instruments, there is a budget for supplies like solutions or whatever, there is a budget for project meetings, there's a budget for traveling, there is a budget for paying salaries and stuff. Does that happen in Australia, or do you have to apply for all these different pieces separately? Like how does that work?
There is a big analogy in Australia. In non-biological or non-health sciences, the Australian Research Council fund all sorts of different types of projects that are multi-year. So the big one would be the Discovery Project, which is 3 years. It funds students and Navy staff, consumables, travel, equipment time, that sort of stuff. Novel cutting-edge discoveries, basically. It can also, the same program can also fund individual researchers, say early career researcher or mid or late career researchers under similar schemes. They've recently introduced a industry style fellowship where it's similar, say, perks to the individual's research, but it's done in conjunction with the industry. So there's all sorts of different funding opportunities in material science. They're all quite large funding schemes, multi-year, salaries included. Smaller funding schemes are more commonly internal. Depending on what you want to do, they're often a lot more targeted. So yeah, we do have a big national funding agency. NLC. Health, there's the NHMRC.
I'm curious about how does the science funding or material science funding works in Australia? How is it structured? But it's good to know that you can get like these long-term 3 years grant.
In brief, material science discovery as opposed to commercialization research is mainly funded through the Australian Research Council Discovery Project Scheme, which is usually about 3 years duration.
Okay.
And it's similar to what we're describing from the DFG.
Okay, interesting. Levi, thank you very much for answering my questions patiently even if I took you away from your point, this has been wonderful. But before I let you go and do your lab stuff or go to your director to talk about the job, one last question. So, what can the followers of the Real Scientist Nano Twitter account expect in the week that you are curating the Twitter account? What can they expect other than beautiful pictures and a coffee shop, hopefully?
Well, we're so excited to say they can expect incredible microscopy images. They can expect atom probe microscopy of incredible interfaces. They can expect atomic scale TEM. They can expect videos of in situ TEM. They can expect incredible biological material science structures using SEM. It's going to be a big focus on microscopy, not only from the University of Sydney, but around the world. All sorts of different types of materials, all sorts of different applications. Basically, all the incredible things you can learn about materials using microscopes and what that means for their real world applications.
Oh, that sounds so cool. This is amazing. I cannot wait to follow your tweets. This is amazing. This has been wonderful. Thank you very much, Levi, for speaking with me, and looking forward to having you again and again and again on Under the Microscope, because who else to talk to other than the microscope ninja himself? So,
Thank you, Pranoti. It's been an absolute blast. Thanks for having me.